Welcome to Unit 9, Part C, Electromagnets and Magnetic Hysteresis. In this video, you'll learn about a magnetic circuit and its components, electromagnets and applications, and magnetic hysteresis and how it is shaped. This figure shows an example of a magnetic circuit. When a current flows through the coil, an electromotive force MMF is set up. The electromotive force Fm is equal to N times I. N is the number of turns of the coil. The MMF drives a magnetic flux flow through the magnetic material. The reluctance of the magnetic material hinders the flow of the flux. This is similar to what a resistor does on the circuit current. Flux is equal to magnetomotive force over reluctance. This is known as Ohm's law for magnetic circuits. In this example, a current of 3 amperes is applied to the 8-turn coil. Therefore, the magnetomotive force is equal to 8 times 3 equal to 24 ampere turns. In Part B, the flux is given to be 240 microvepers. We can apply this formula to calculate the reluctance. Divide the magnetomotive force 24 ampere turns by the flux. We can get the reluctance to be 100,000 ampere turns per vapor. Example 2. Determine the flux established in the magnetic path. If the reluctance of the material is 500,000 ampere turns per vapor. To find the flux, we have to first calculate the magnetomotive force N times I. The number of turns N is given to be 5 turns, and the current is 2 amperes. So 5 times 2 is equal to 10 ampere turns. Apply Ohm's law of magnetic circuits to calculate the flux. The magnetomotive force is 10 ampere turns. The reluctance is given here. So the flux can be calculated to be 20 microvepers. A magnetic circuit path can consist of more than one material. For example, a piece of ferrite with an air gap. The reluctance of the air gap can be a few hundred times higher than that of the core material. Therefore, high electromotive force is required to drive the same amount of flux go through a magnetic circuit with an air gap. Smaller the air gap, smaller the requirement of the magnetomotive force to drive the same amount of flux. The flux density B is affected by a few parameters of the solenoid. For instance, B is proportional to the number of turns of the coil. The flux density B is also directly proportional to the coil current. But B is inversely proportional to the magnetic path length L. B is also directly proportional to the permeability of the material of the magnetic path. This formula sums up all these factors, and we can use this formula to calculate the flux density inside the solenoid or at the two ends of the solenoid.